Good day and thank you for being here today. I'm Daniel Ranque and I'm here to talk to you about our study on the design and development of energy harvesting ramp through brushed DC generator using gear system. These are the topics or keywords of our paper. First, we have energy harvesting through kinetic energy. It is the process of converting an environmental, kinetic, or vibration energy like wind, waves, vehicle movement, machinery vibration, human motion, etc. into electrical energy that can be used to power small and low energy electronics. Second is gears. They are used to transfer motion and torque between machine components in mechanical devices. Depending on the design and construction of the gear pair employed, gears can change the direction and movement and/or increase the output speed or torque. Third is brushed DC generator that uses configuration of wound wire coils, that armature acting as a two-pole electromagnet. And lastly, a boost converter is one of the simplest types of switch mode converter. As the name suggests, it takes an input voltage and boosts it or increases it. For our objectives, to design and develop an energy harvesting ramp through brushed DC generator using gear system and utilize the energy harvested in the form of DC source. To build an energy harvesting ramp through brushed DC generator using gear system enclosed in a casing. To perform monitoring on the integrated harvesting charging circuit, to utilize the charged battery in an electronic device and to determine the amount of time it can supply the device. Figure 1 shows the conceptual framework of the system. The input is purely kinetic energy which uses the mass of vehicles that can be captured by passing through the ramp. This kinetic energy can now be processed with the use of a DC generator that will convert the mechanical energy to electricity at a faster pace. The output voltage of the DC generator is converted to 220 AC voltage using an inverter. Figure 1.1, the system process shows that the mass of a vehicle is fed first into the ramp to produce an impact that will make the gears rotate and produce electricity. Now the produced electricity from the DC generator will go through the boost converter to increase the magnitude of the output voltage before it goes directly to the transistor and stores inside the rechargeable battery. The data logger is used to record the voltage and current running through the system. Once the battery is energized, the DC voltage that it produces will be converted to an AC voltage using an inverter to supply a specified load such as radios, smartphones, LED bulbs, etc. The dimensions and design gear system were generated using AutoCAD and Fusion 360. Figure 2 shows the working mechanism of the crank generator. The ramp drives the rack through the guide shaft, rotating the one-way ratchet gear which then rotates the gear train. Figure 3 shows the side and top view of our prototype. The prototype has a base of 52 by 76 cm with a height of 13.5 cm from the base plate to the top middle plate. Shown on the side are the components of the actual prototype. It illustrates the top view of the prototype connected to the circuit box, which includes the line switch, inverter, PCB, rechargeable battery, metering device, DC generator output wire, and AC outlet. Figure 4, the researchers developed an integrated harvesting circuit to harness the produced energy from the made kinetic energy. It shows the PCB board as the center of the circuit connected to the individual electronic components of the prototype and the mechanism. In this figure, the researchers used Fusion 360 for design and precise fabrication of the gears and mechanism of the prototype. In Figure 7, the researchers used a gear train simulation with the use of geargenerator.com. This provides us with the theoretical setup of our gear train with computation that allows us to input the initial speed of the driver gear and compute for the RPM of the driven gear. This figure shows a custom-made circuit box to place all the components. The circuit placed inside the circuit box along with the battery, inverter, and appropriate switches of the circuit. The meters are placed in such a way that it can be all viewed on one side of the prototype. This figure shows the demonstration of a vehicle passing over the working prototype. Table 3.3 shows the weight variation of the vehicle that commonly passed through the testing area at the time of their testing, where we recorded RPM, torque, and angular velocity. Weight is based on the curve weight model of the vehicle. Torque can be computed using the radius of the gear multiplied by the weight. RPM is measured using the tachometer, and angular velocity can be computed using the acquired RPM multiplied by 2 pi over 360. The top two graphs shows the relationship between the weight versus the generated RPM and angular velocity. As seen from their progress, both the RPM and the velocity are directly proportional to the weight of the vehicle. Next is the bottom two graphs where we compare the torque versus the weight and the angular speed. And as seen clearly, both are directly proportional to one another. The voltage and current generated is based on the recorded data using the data logger. Each has a remark to whether it's valid or invalid. A minimum of 2-volt output from the generator to be identified as valid, otherwise invalid. On the other hand, a minimum of 0.85 to 1 amp must be generated by the generator to be identified as valid as per EECE 60086 battery standard, specifically primary batteries as a basis for the current charging the battery, or otherwise invalid. Based on the table, the minimum current generated is 0.9 amp and the average current generated is 1.243 amps and 5.2 volts for the average voltage. The built experimental model has laid out the ground to see the feasibility of installing an energy harvesting ramp. A survey of vehicular traffic at the entrance of Park Place Executive Village, Gate 1, has been done. The testing was from 8 a.m. to 1 p.m. as instructed by the subdivision management. This type of energy can be considered as limited energy source since its output depends on the traffic of vehicles. Hence, the expected power output was computed based on the number of vehicles as shown in column 5 of table 3. The obtained results produced an average power output of 211.19 watts per day for 5 hours of testing and a total of 2,534.24 watts. The average energy produced per vehicle was compounded and shown in Table 3, voltage and current monitoring. To summarize the earlier slide, the research extracted the important details that showed the daily traffic level passing through the ramp with an average of 31 vehicles per day. As seen on the graph, the number of vehicles dramatically increasing and decreasing. This is to prove that the researchers have no control over the traffic. On the other hand, the daily power generated consists of a total of 12 days. The power generated depends on the number of vehicles that can be seen on the graph of daily traffic level, and the average daily power generated for 31 vehicles is 211.19 watts. This figure shows the correlation relationship. Its value always ranged between -1, a strong negative relationship, and +1, a strong positive relationship. Values are at those or to 0 imply a weak or no linear relationship. Correlation coefficient values less than positive 0.8 or greater than negative 0.8 are not considered significant. Based on the graph, weight and power generated was a positive correlation. As the weight increases, power generated also increases. On the other hand, using Pearson's correlation formula, the value of R is equal to 0.9881, proving that the weight and power generated has a strong positive relationship. On the other hand, based on the graph, RPM and power generated have a positive correlation. As the RPM increases, power generated also increases. On the other hand, using Pearson's correlation formula, the value of R is equal to 0.9814, proving that the weight and power generated has a positive relationship. This table shows the battery discharge rate using an inverter. The table consists of 10 different types of electronic devices. Based on the results, the discharge rate can be computed using the battery backup time equation. As seen on the table, most of the test was done using an LED bulb. This is to maximize the use of the battery at a slow discharge rate. For the conclusion, the research created a working prototype to demonstrate the idea for a system that can both harvest energy from the weight of the vehicle and reduce the vehicle speed. The average mechanical input per vehicle is 9.24 watts, and the average power output per vehicle is 6.74 watts, giving an operational efficiency of 72.94%. Gave enough energy to charge up a 12-volt, 7-ampere-hour lead-acid battery for 58 hours using the weight of the vehicles. The objectives presented, the results from the prototype, and the main objective of the study are achieved and produce acceptable results. The energy harvesting device generated an average output voltage of 5.2 volt per vehicle and generated current which averaged 1.243 amps per vehicle. A 12-day test was conducted to fully charge the battery from discharge state. The total power generated per day is 211.19 watts and the total of 2,534.24 watts for the whole duration. Side view. This shows the side view of the prototype when a force is exerted on the ramp. Road trial. This is one of the trials showing the working prototype. Subdivision gate trial. This is a recorded video of the working prototype passed through by 2 vehicles. As they pass through, a researcher records the data produced in the meters. Mats were placed under to reduce the movement of the device. Powering device, 9-watt light bulb. Lastly, this shows the prototype powering a light bulb. The test starts at 8:30 a.m. At 10:08, 3 bars are left. At 12:02, 2 bars are left. At 1:50, 1 bar is left. And at 3:43, 0 bars are left, and concludes the test. Thank you for watching.